This challenge problem overviews modeling the spread of a wildfire by Jacy, Morgan, and Oumar. Our model can be used to predict the movement of a wildfire, thus supporting decisions on resource allocation and firefighting strategy. Wildfires devastate ecosystems all around the world. They destroy plant life, displace wildlife, and disturb soil stability, and degrade air and water quality. This poses significant risks to infrastructure, public safety, and long-term land recovery. The model aims to predict the motion of the fire front over time, simulate fuel depletion as combustion occurs, and assess how each environmental firefighting factor affects this spread rate. The model is a system of uncoupled linear ODEs with the following assumptions. The wildfire advances in the positive X direction only. The front propagates as a moving boundary where the fuel burns only behind the fire front. We assume that there is a uniform fuel load, terrain, altitude, and firefighting measures. That is, water and retardant are applied uniformly and oxygen only changes with wind input. The fire's reaction rate depends on moisture, wind, water, and retardant as provided by equations shown in the next slide. Equation 1 defines the rate of burn, which governs this model, where Wf is the fuel density, K0 is the base burning rate of the fire, and K is defined by equation 8. K0 accounts for when all of the other effects go to 0. Equation 2 approximates the oxygen concentration using the effect of the wind on the fire. Equation 3, 4, 6, and 7 take into account moisture content, retardant, and water. And equations 9 and 10 indicate whether the position is behind or in front of the fire front.
This wildfire simulation shows how the fuel density changes over time with the fire front. As you can see, this simulation shows the greatest amount of fuel density is where the fire front's current position is, and the lowest amount is ahead of the fire front. This graph shows the effect moisture content has on the spread of a wildfire at 3, 7, and 15%. The fire spreads more rapidly at lower moisture contents, where the grass is drier and burns easier and faster. Higher moisture content suppresses the fire and forces the flame to expend energy evaporating the water, which slows combustion and reduces fire line intensity. With this next graph, we can see how wind speed affects the rate of burn at 0, 5, and 10 meters per second. The fastest spread of the fire occurred in windy conditions. Strong winds increase convective heat transfer, oxygen concentration, and flame tilt, and this allows flames to preheat fuel ahead of the fire front. This next graph shows how water applied to the fire slows the fire front movement, supporting reduced combustion rate via lowering temperature and limiting oxygen. The fire spreads the fastest when no water is added, and XF of T increases linearly. Strong suppression occurs when a heavy amount of water is applied, stalling the fire front movement. Interestingly, with moderate water, the curve bends downward shortly after ignition, and there is a noticeable slowdown in the fire front movement, thus demonstrating strong exponential suppression in the model. Lastly, this figure shows how retardant can inhibit the spread of a wildfire when used as a firefighting measure. Retardants chemically inhibit pyrolysis and ignition, leading to a reduction in the effective burn rate.
The modeling result shows the wildfire spread is strongly influenced by environmental conditions and suppression actions. The rate of fire spread shows to decrease when moisture content is higher, when it's slower, when water and fire retardant are applied, and when oxygen is limited. This behavior would match real wildfire observation where dry, windy conditions lead to rapid fire growth and suppression resources are applied early. This emphasizes the importance of monitoring this factor and strategically applying suppression to manage wildfire spread. For the conclusion, certain conditions could be applied to model to increase accuracy, one of which is to account for the difference in fuel type Alternatively, the altitude and terrain will help determine how the fire move across different environments. By modeling the spread, this, by modeling the spread of the firefighting and reduction effort become more effective through a better understanding of which methods to use and the most critical area of the fire. Fighting the fire where the spread is faster ensures the opportunity for the fire to spread across the greatest distance is halted before causing more damage. All in all, we learn how to formulate and simplify a complex model to create code, illustrate our finding, and we learn a heck of a lot about wildfire.
And these are our references. Thanks.